Chapter 7 is the human population. So in the beginning of this chapter, it talks about China's growing population. China has about 1.3 billion people, 20% of the world's population. The U.S. has 307 million, significantly less, but we're the world's largest consumer of resources. China eventually may surpass the U.S. in consumption and pollution, the largest emitter of carbon dioxide and sulfur dioxide, and they consume 1/3 of the commercial fish and seafood. But the policy that comes up with population is that since the 1970s, China has had a one-child policy. You are financially rewarded if you only have one child, and if you have 3 or more, sanctions are imposed on you. It's been controversial. There's been abortions and sterilizations, but the fertility rate is now 1.6 births per woman. But resource consumption increases as standards improve. So as China becomes more industrialized, they're still polluting at a same or higher rate because they're now having more cars and more appliances. Between 1985 and 2002, the population increased 30%, but their car use increased by 500%, and they're the second largest consumer of petroleum. They have higher fuel efficiency standards than the United States, but 16 of the 20 worst polluted cities are in China. So there's a lot of things that play into population, not just the number of people you have, but how many resources they use. And we're going to examine these through the course of this chapter. Human population is growing exponentially. You can see in these two graphs, especially this inset here recently of how quickly our population has been growing. Scientists disagree on Earth's carrying capacity. So Thomas Malthus had a conclusion in 1789 that the human population was growing exponentially while food supply is growing linearly. Let's take a look at these two graphs. These are the graphs he had. So if our population here is growing exponentially, but our food supply is growing linearly, we will have some sort of food deficit that we will have. Every 5 days, just for statistics, the global population increases by 1 million. 1.8 million people are born every 5 days and 800,000 die. This is due to increased agriculture and sanitation. So the reason we are able to continue to have this exponential growth is that there's this innovation. So the opposing view to Malthus' idea is that increased humans also equals increased intellect, which leads to innovation. So humans can alter the carrying capacity. Innovations that initially allowed the population to increase were things like arrows for hunting, oxen-drawn plows, and then we moved to mechanical harvesters. So as we increase our population, we need to increase the way that we're able to feed them, and that innovation allows this food supply line to be increased in order to keep us out of a food deficit. Projecting future populations, the population is increasing. The growth rate has started to decline. And when we look at 2050, the low projection is 7.7 billion. The high projection is 10.6 billion, but most likely will be around 9.1 billion. Changes in population size. So factors that increase a population, and when we have demographers look at trends in specific countries, this is what they have to look at. So population size is increased due to immigration and births, and population size is decreased due to emigration, which is moving out, and deaths. The equation that deals with this is national population growth rate is crude birth rate plus immigration minus the crude death rate minus the immigration. And this should be plus immigration, and then plus emigration. So change that to a plus right there. But we do subtract these two quantities. And we divide by 10 to make it into a percentage, because crude birth rate and immigration rate, all of that is done per 1,000. So if we go ahead and divide by 10, you sort of have a denominator of 100, which is going to turn it right into a percentage. So let's look at immigration and emigration first. The difference is the net migration rate. You have to be able to calculate it. Positive net migration versus negative net migration has to deal with do we have more people moving in versus moving out. And it's still important to look at where they're going, because global population isn't changing by people moving around. And if we're looking at changes in population size, the blue is populations that are increasing, green is staying stable, and the brown is decreasing in population. And the gray, we're unsure of exactly what's going on with their population. We don't have enough statistics or data to know. You can get an idea of where global population is. Crude birth rate is the number of births per 1,000 individuals, and crude death rate is the number of deaths per 1,000 individuals. And here's some important formulas for this chapter that we need to be able to use. They're pretty easy. Global population rate is crude birth rate minus crude death rate. You don't have to include immigration and emigration because we're looking at the whole globe, so it doesn't really matter where they live. National population growth rate, here's the correct version of that equation. Crude birth rate plus immigration minus the crude death rate plus emigration, which is leaving, divided by 10. And then we have another equation that's pretty important called doubling time. Doubling time is the time it takes for a population to double. And we can use this rule of 70. Doubling time in years is just equal to 70 divided by the growth rate. And it works for any population. It's a really easy equation, and it's one that shows up a lot on the APES test. If we look at some birth rates by country, we can see where some of those higher birth rates are in the darker blue, and the lighter colors are much lower birth rates, just so you can have an idea of how populations are. Looking at fertility, some terminology that we have. The total fertility rate is the estimate of the average number of children that each woman in a population will bear throughout her childbearing years. Replacement level fertility is a little bit different. It's the fertility rate required to offset the average number of deaths in a population and for the current population to remain stable. Typically, replacement level fertility is 2. You replace your parents. But sometimes it needs to be higher in developed countries due to pre-reproductive mortality. So if you think about people dying before they reach childbearing age, it takes into account that. So total fertility rate is how many babies people are having, whereas replacement level is how much required to offset those average number of deaths. Life expectancy is the average number of years that an infant born in a particular year in a particular country can be expected to live, given the current average lifespan and death rate in that country. So how long can an infant live if they live in that country? And if you look at this diagram, you can see the darker colors have longer life expectancies, whereas the lighter colors have much lower life expectancy. If we look at resource consumption as related to that, people that live longer will consume more resources over the course of their lives. This is reported in 3 ways when we look at life expectancy. We look at the life expectancy of the overall population, so we average the males and the females, and we always also look at the life expectancy of males and the life expectancy of females separately. If we're going to look at some mortality, we have some things such as infant and child mortality. So infant mortality is the number of deaths of children under age 1 per 1,000 live births, and child mortality is number of deaths of children under age 5. Infant and child mortality is directly related to health care, food supply, drinking water, sanitation, and moderate pollution. Globally, the data on this is 46 per 1,000, but in the United States it's 6.6 per 1,000, and Sweden is 2.5, so you can get an idea of what some of those mortality rates look like. If we factor in now aging and disease, a country can have a high death rate because it has a large number of older individuals. So crude death rate and life expectancy are not directly linked. So if you have a lot of elderly in your population, your crude death rate is higher. Diseases regulate the human population. According to the World Health Organization, the number 1 disease that affects human population is heart disease, and the number 2 is infectious disease. And the one that's the most significant in the past had been tuberculosis and malaria, but now it's HIV. Between 1990 and 2007, HIV and AIDS killed 22 million people. It affects people ages 15 to 49, so it has a more disruptive effect because those are childbearing years that are being affected. It affects infant mortality, child mortality, population growth, and life expectancy. There's 33 million people living with HIV as of 2009, and 22 million of those people live in Africa. So that's a significant statistic right there. Looking at age structure diagrams. This is a good place for us to pause, and I'm going to start the next video with age structure.